Hi everyone, it's another beautiful day in statistics land during the COVID-19 epidemic, so yay! I'm making this video to help explain Anova and give an example of an Anova problem. So let's jump right into it. Remember, Anova stands for analysis of variance. We're going to use it to test whether or not means are the same. Okay, so moving this out of the way, moving this over here, we have our detailed steps for a hypothesis test, and we have our problem. After 3 weeks of the following treatments, meaning medication, exercise, and diet, each person's blood pressure is recorded. Test the claim that there is no difference in the means. Use a significance level of 0.05. So what this problem is saying is that we are trying to use medication, exercise, and diet to see if they have any influence on each person's blood pressure. So this is the reduction in blood pressure, meaning how much the blood pressure went down. Looking at the numbers, we can see that 10, 12, 9, 15, 13, 6, 8, 3, 0, 2, 5, 9, 12, 8, and 4. It definitely seems like exercise has what is going to be a lower mean because medication has much higher numbers. Diet seems to be falling kind of spread throughout. So since we have some low numbers and some high numbers, they're going to influence the mean a lot and probably give us a middle. This one should stay pretty low and this one should stay pretty high. Okay. So now that we have that kind of summarized in our head, maybe have an expectation of what we might get out of this test so we can have some intuition when we get to the testing part of this hypothesis and see whether or not we're right. So our first step is to ID the claim. The claim is that the means are all the same. Test the claim that there is no difference in the means. The opposite would be that the means are all different. Okay, H0 and HA will always read the same for these kinds of tests. It's that the means are all the same, which you can write as mu1 equals mu2 equals mu3. Remember, we have to have at least 3 means to run one of these hypothesis tests. Or you can just write it in words, that the means are all the same. Okay, the opposite of that would be the means are all different. These will always be the cases for H0 and HA when we're running an Anova test for seeing whether or not the means are the same. H0 will always be that they're the same. HA, or the alternative hypothesis, will always be that they're different. Step 4 is to figure out what alpha is, and it says that we are going to use a significance level of 0.05, so that is our value for alpha. Step 5 is to ID the test statistic equation and the function in Excel, and here we're going to use the FStat for the Anova test, and we're going to use the data analysis pack in Excel, which is awesome news because it means that we don't have to do any math, and we don't have to figure out the p-value and the critical value because when we run this data analysis tool pack, it's going to find those for us. Okay, so let's jump into that and start. So the first thing you need is the data analysis tool pack. So I'm going to show you how to grab that. So I have it already. It shows up right here. So you can double check before you try and grab this if you have it. So just pause the video, go to the data tab in the ribbon and go all the way over to the right and see if you have a data analysis tool pack hanging out over there. If you do, then you can skip the next steps. But if you don't see this data analysis tool pack, then you need to go download it with me. So if it's missing, you've got to go grab it. You're going to go to File and then Options. And right here, you'll have all your options for Excel. This data analysis tool pack is an add-in. Okay, and you'll see it down here. It'll probably be in your inactive. I've already turned mine on, so it's in the active applications for me, but yours should be down here in the inactive. You want to just select the data analysis tool pack, and here's a super important part. You do not select OK. You need to select Go. And then that will bring up this dialog box, and you just make sure the data analysis tool pack has a check mark next to it, and you hit OK. So one more time, when you get to Options, and then add-ins and data analysis tool pack, do not hit OK. Hit Go instead, and that's where you'll get this add-ins dialog, and you'll be able to select analysis tool pack, which I realize I did not spell right because they spelled it weird, and hit OK. And then you should have this appear right here. Okay, when it appears, there should be a menu here, which is probably a bit small for you to see, but I don't know how to make it bigger. So right now it says Anova single factor. You may have to scroll up a little bit to get to that. I think it usually starts right here at Anova 2 factor with replication. If that's all you're seeing, then you need to scroll up once. And Anova single factor is at the very top of the list. Select OK, and you'll get a new dialog box. We want to give it an input range, so we're going to select this little up arrow. and then we're going to go highlight our data and select the down arrow. And now it should show the range for your data. Our data is grouped by columns, as I have a column title and data underneath each column. I do have labels in the first row, which is medication, exercise, and diet, so I want to make sure that I have a check mark in the labels in the first row box. And it's going to ask me what alpha is. That's 0.05, so I need to make sure that it matches what the problem gave me, because sometimes in the homework you'll get a different value for alpha, and you'll need to edit it right here. Okay, and then you want to select an output range. So you can just do the default, which I think is new worksheet. That'll appear in a different area from where you're currently working, and so it's usually better just to select an output range. And then just select a single box anywhere in your sheet, and it'll input the output for your analysis there. So I'm going to select just a single box next to my step 6 information. This is going to take up a lot of room, so you want to make sure that you're selecting a single box that has a lot of room to the right and below it. I'm going to go ahead and hit the down arrow and then just hit OK. And now it has given me a lot of information. I am going to make this larger so that we can read it. All right, so I've got medication, exercise, and diet. It's given me a count, a sum, an average, and a variance. So I can see that the average right here, those look pretty different as I thought they would be. This one was small, this one was right in the middle, and this one is pretty high. It's given me the information I need for my F statistic, which is the variance between groups and within groups. And it's given me an F statistic and a p-value and a critical value. Unfortunately, these are a little cut off, so I'm going to go ahead and widen these columns so I can get some more digits from that. Got a p-value and a critical value. So I'm just going to go up and I'm going to copy paste it into my step 6 area. So let's see, I've got an F, that's my test statistic. I've got a p-value, that's my p-value. And I've got this F crit, and that is my critical value. So going back down to the output, I'm just going to highlight those cells real quick just to emphasize what we got out of this table. Okay, and then it also gave us a nice summary of our data, including the variance so that we can check our requirements, and the averages and the counts. I'll just go ahead and highlight that too. That's all important pieces of information. Okay, so now what about our, can't think of the word, the rejection region. We usually tell what tail we have from the alternative hypothesis, but as I said, it's in words now. Usually it's in math, and the math symbols tell us whether or not we have a right tail or a left tail or two tails, and this one is not. So how do we know if we're right-tailed or left-tailed or two-tailed? And that goes back to the equations and the way we're calculating the F statistic. If you go back and watch the video on goodness of fit, I explained there why goodness of fit tests are always the same and they're always right-tailed, and this is going to follow the same logic. So what we want to do is we want to find out if these means are the same. Okay, if they're the same, then when we do subtraction between them, we will get a little number. Okay, and if they're all different, when we do subtraction between them, we will get a much larger number. So if they're all different, we'll do subtraction and get a big number, which means we'll end up on the right-hand side. When we're on the right-hand side, we should reject the null hypothesis, which says they're the same. When we're all the same, we'll do subtraction, get a little number. We'll end up on the left-hand side of the number line. And over there, we want to fail to reject the null hypothesis because the null hypothesis says they're all the same. So when we do subtraction, we get a little number, then they're all the same. So we want to fail to reject the null hypothesis. Okay, when we do subtraction, they're all different. We get a big number. We want to be able to reject the null hypothesis when we end up on the right-hand side. So the same as before, this is going to end up as a right-hand or a right-tailed test. So I just want to go and look at the calculations just a little bit. We're not going to go into detail here, but I just want to talk about where the subtraction is coming from in the F statistic. So I'm going to go pull up the OpenStax book for statistics, and we're just going to look really quick at the F distribution. There's a ton of math in here, and I don't want to get into it in detail because we don't need to do these calculations in our class. But I do want to point out that we're looking at the stuff which is variability between groups, which is going to have subtraction. We're going to be looking at the total sum of squares, which also involves subtraction. We're going to look at explained variation, which involves subtraction. And we're going to look at unexplained variation, which involves subtraction. Okay. Then we're going to look at the mean, a variance explained by the difference between groups, and the mean squared variance estimate that is due to the change or unexplained. Okay. Those are ratios. And then the F ratios of what we did subtraction of. The F statistic is a ratio of those two ratios. So it's like a double fraction. Okay, so the F statistic is MS between and MS within, where MS is standing for the mean squared and the mean square. Okay, so this is, the F statistic is based on a ratio, a double fraction ratio, that is based on a bunch of subtraction. So it really comes back down to when the difference is large, we end up on the right-hand side. So we want to reject the null hypothesis. When the difference is small, we end up on the left-hand side. We want to fail to reject the null hypothesis. So this will always be a right-tail test. So let's go back to Excel and let's go ahead and draw our distribution and put on all the information we got from running that Anova single factor analysis in Excel. So I'm going to do my very best to draw this. The F distribution looks very similar to the chi-square distribution. So we're going to draw essentially the same shape. We need our critical value, which this is telling us is 3.89 about. This area right here is the same size as alpha, so this is alpha is equal to 0.05. That's the size of our rejection region. Our rejection region starts at 3.89. Our test statistic is way over here at 9.17 about. And our p-value is about 0.0038, which is much less than 0.05, our value for alpha. So highlighting our rejection region. Ooh, that's hard to do. Okay, and then our p-value fits in here. Okay, so this is telling us that our critical value, or sorry, our test statistic falls in our rejection region, and our p-value is smaller than alpha. So either way, we got the same conclusion, which we always should, that we are going to reject our null hypothesis. Okay, so in step 7, we reject the null hypothesis for one of two reasons. Our test stat falls in the rejection region, which it does, or our p-value is less than alpha, which it is. So we're going to go back up to our H0 because we rejected it. We will turn it red. Okay, and then we have to double check, does that match the claim or not? So this says the means are all the same. The claim says that the means are all the same, so we're going to reject that as well. So if this had been if it had been the means are all different, then we would turn it green because we've rejected that the means are all the same. So one more time through that, we ran our Anova analysis in Excel, which is where we got these values. We decided this is a right-hand tail test and it will be always. Okay, we put in our value for alpha, our p-value, which we found was less than alpha, our critical value, and our test statistic, and we found that it landed in the rejection region. So we rejected the null hypothesis. We went back up and turned the null hypothesis red because we rejected it, and then we compared it to the claim, and it matches, so we're also going to reject the claim. So here we're going to say that the data does not support the claim that there is, the data does support the claim that there is no difference between the two means. So we should say does not support the claim that there is no difference between the two means. Going back up and double checking, zooming out a little so I can see it all at once. We have turned the claim red, so we're not going to support it. So we've written that the data does not support the claim that there is no difference between the means. Okay, that's based on the fact that our test statistic fell in the rejection region, so we rejected the null hypothesis. We turned the null hypothesis red. The null hypothesis is the same as the claim, so then our conclusion says the data does not support the claim. And then we just rewrote the claim that there is no difference between the means. Okay, so I hope to see you in the discussion boards. Use the Hey Professor board. Contact me through Pronto. Send me an email if you have questions, and I'll see you soon.